Guatemala, a land renowned for its vibrant culture, ancient Maya ruins, and dramatic volcanic landscapes, also holds a fascinating geological secret: vast Ophiolitic belts with significant potential for nickel and cobalt deposits. Imagine a journey through time, delving into the very crust of the Earth to uncover how these valuable resources came to be, shaped by millions of years of intense geological activity. This is the story of Guatemala's dynamic subterranean world, a narrative of shifting plates, fiery eruptions, and the slow, steady hand of weathering. The geological canvas of Guatemala is nothing short of spectacular. It's primarily divided into four main physiographic regions: a narrow Pacific coastal plain, an active volcanic province stretching northwest, the rugged Central Cordillera running east-west, and the expansive Petén lowlands. The Central Cordillera, in particular, is a treasure trove of geological history, harboring some of Guatemala's oldest rocks. Here, you'll find ancient Paleozoic schists and pegmatites, alongside vast stretches of Cretaceous carbonates and, crucially, the very Ophiolitic belts that whisper tales of bygone oceans. At the heart of this geological drama lies the Motagua Suture Zone. This isn't just any old fault line. It's a colossal scar where tectonic plates have grappled for eons. Specifically, it marks a significant boundary within the northwest corner of the Caribbean Plate, a region where fragments of ancient oceanic crust and upper mantle, known as ophiolites, have been thrust onto the continental landmass. It's like finding pieces of the deep ocean floor perched high in the mountains, a geological marvel. Within this suture zone, several distinct Ophiolitic complexes have been identified, including the North and South Motagua, Juan de Paz-Los Mariscos, Sierra de Santa Cruz, and Baja Verapaz complexes. Each tells its own unique story of Earth's relentless churning. The birth and evolution of these Ophiolitic belts in Guatemala involved a fascinating four-phase process, a true geological epic. First, deep beneath the ancient oceans, magma chambers formed. Within these fiery cauldrons, molten rock underwent fractional crystallization at temperatures below a sizzling 1050 degrees Celsius, forming ultramafic rocks, the very foundation of oceanic crust. Then came the dramatic second act, obduction. As the Caribbean Plate collided with other massive tectonic plates, these dense ultramafic rocks, originally part of the ocean floor, were peeled off and thrust upwards along immense faults. This titanic collision was so powerful that it forced oceanic lithosphere to ride up and over continental crust. As these rocks began their slow, upward journey, a crucial transformation, known as serpentinization, began. Olivine, a common mineral in ultramafic rocks, started reacting with heated seawater, a process that would reshape the very fabric of these once oceanic fragments. The third phase saw serpentinization in full swing. This hydrothermal process completely transformed the original olivine and pyroxene minerals within the ultramafic rocks into a new suite of minerals, primarily serpentine and brucite. This is where things get interesting for resource explorers. Petrographic analyses of rocks from these Guatemalan ophiolites have revealed the presence of nickel-bearing minerals, including aurorite, pentlandite, and even nickel-bearing serpentine and magnetite. It's a testament to how geological alchemy can concentrate valuable elements. Finally, the fourth phase brought about oxidation. As the serpentinized rocks were exposed to the Earth's surface, they underwent intense weathering. Olivine rocks oxidized, leading to the formation of iron-rich minerals like goethite and, eventually, the distinct laterite soils, sulfides, also present in these rocks, reacted over time, contributing to the rich, reddish-brown hues characteristic of these weathered profiles. These laterite soils, thick and often extending for tens of meters, are precisely where significant nickel-cobalt deposits accumulate. They occur in various forms, from in situ deposits, which are essentially weathered bedrock, to alluvial-diluvial types, transported and redeposited by water and gravity. Finding these hidden nickel-cobalt riches requires a sophisticated toolkit of exploration techniques. Geologists don their explorer hats and embark on systematic geological mapping, often covering vast areas of 10,000 square kilometers or more. They collect geochemical samples, analyzing them for a wide array of elements, including target elements like nickel and cobalt, and pathfinder elements that indicate the presence of ore. Modern tools, such as portable X-ray fluorescence (PXRF) devices, are game changers, allowing for rapid field testing and immediate insights into the mineral composition of samples. It's like having a miniature lab in your backpack. Geophysical surveys play a crucial role in peering beneath the surface. Ground-penetrating radar GPR helps map subsurface clay layers and the depth to unweathered bedrock, which is key for understanding laterite profiles. Airborne surveys, like aeromagnetics, can detect subtle variations related to basement structures that influence the distribution of deposits. Remote sensing, using satellite imagery and aerial surveys, helps in identifying linear features that can indicate faults or fractures controlling mineralization. All these methods are carefully integrated, often with 3D modeling, to pinpoint the most promising exploration targets. And, of course, meticulous quality assurance and quality control QC programs are essential to ensure the reliability of all collected data. Sometimes, helicopters are even employed to make regional sampling in rugged terrains a more efficient, albeit slightly less grounded, affair. However, the path to unlocking Guatemala's nickel-cobalt potential is not without its challenges. The Great Laterite Challenge refers to the inherent difficulties in mining and processing these deposits. Compared to nickel sulfide operations, laterite mines, especially those using high-pressure acid leach HPAL processing, have a significantly larger environmental footprint. They generate higher greenhouse gas emissions, partly due to energy consumption and the need for large quantities of sulfuric acid for processing. There are also social and environmental concerns tied to the sheer scale of the operations, the disposal of vast volumes of tailings, and the potential for spills. History is littered with examples of projects, like Goro in New Caledonia or Ramu in Papua New Guinea, that faced years of opposition, sabotage, and legal battles due to these very issues. It turns out that convincing local communities and environmental watchdogs that you can extract resources responsibly is harder than finding the resources themselves. These operations often face hurdles like operational underperformance, budget overruns, and construction delays. Yet, despite these formidable challenges, the global demand for Class 1 nickel, particularly for battery cathode chemistries, means that more of these complex laterite deposits will likely be developed in the coming years. Guatemala has long been a focal point for geological inquiry, attracting worldwide attention to its dynamic processes. The compilation of geological bibliographies, for instance, shows a significant increase in published material since 1965, spurred by collaborative geological mapping programs and continuous volcanic activity. Major events like the devastating 1976 earthquake focused a global spotlight on its seismicity, while the deep-sea drilling project offshore Guatemala provided unprecedented insights into the Middle America Trench and the mysteries of subduction zones. Research has spanned everything from volcanology and plate tectonics to paleontology and even petroleum exploration, though, humorously, information on the latter has been kept rather tightly under wraps. Beyond the quest for minerals, lateritic soils themselves are remarkable. Formed by the relentless tropical cycle of wet and dry seasons, they are clay-like and rich in iron. What's truly astonishing are their transformation. When moist, they're surprisingly easy to cut and excavate, but once they dry, the iron salts within them create a rigid structure, almost as strong as concrete. This unique property has been harnessed for centuries. Ancient monuments across Southeast Asia and India stand as testaments to their durability. Perhaps the most famous, or infamous, example is the network of Cu Chi tunnels in Vietnam, which famously withstood carpet bombing thanks to the almost concrete-like rigidity of the lateritic soil when dry. It just goes to show, nature sometimes provides the best engineering solutions, even for guerrilla warfare. In essence, Guatemala offers a living laboratory for earth scientists and a challenging, yet promising, frontier for resource explorers. Its complex geological history, marked by the powerful dance of tectonic plates and the slow, transformative power of weathering, continues to yield valuable insights and crucial resources. Understanding these deep earth processes isn't just academic. It's about navigating the future of our planet, one laterite deposit at a time.
Are you passionate about geology and earth sciences? Explore geology with me on YouTube. Subscribe, like, and share my content.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.